Hello, class. We are going to move on to our third type of bonding today. The first two types we looked at were covalent bonding, the sharing of electrons, and then ionic bonding, which was the transfer, actually giving up an electron. Now we're going to look at the third type of bonding, and that is metallic bonding. You can see all the different properties of metals. We remember malleable, ductile, luster. They conduct electricity and they conduct heat. This type of bonding is going to explain those 5 properties. So our objectives, we're going to describe the electron C model of metallic bonding and explain why metals are good electrical conductors. We're going to explain why metal surfaces are shiny. We're going to explain why metals are malleable and ductile, but ionic crystalline compounds are not. All right, let's go ahead and start with the metallic bond model. We know the highest energy level of most metal atoms, they are relatively empty. They are occupied by very few electrons. Some of them have 1 electron in the s block, where you can see right here, you have the 2s and the 2p. There's 1 electron in that whole entire outer energy level. And that's typical of anything that's in group 1. And even when you get into something that's in group 2, your alkaline earth metals, you have 2 electrons. So that whole outer energy level is pretty empty. So the p orbitals are generally vacant. There's nothing there. Even when you get into the d block metals, you have empty d orbitals. So what happens is there tends to be a lot of space. And what that does is create what's called an overlap. So the orbitals from one atom overlap the orbitals of another atom, allowing the electrons to move from one atom to the next freely. That's called delocalized electrons. It means the electrons don't belong to any one atom, but they move freely from one atom to the next. I'm going to show you a little something on the next slide of how that actually happens, but it all has to do with this right here. These empty orbitals, those vacant places where there's overlap, allowing the electrons to move from one atom to the next. And you can see if you were to picture one metal atom to the next, this electron you would think belonged here, but since there's an overlap in the orbitals, this electron can move from this atom to this atom to this atom, and so on and so on. So the electrons generally become shared by all of these atoms, all those outermost electrons. That is your sea of electrons. The electrons can move freely from one metal atom to the other, and it creates a crystal lattice in the middle, kind of like an ionic bonded element or compound. You get this crystal lattice. But here the electrons can move freely, whereas in ionic they cannot. All right, metallic bonding, chemical bonding that results from the attraction between metal atoms and the surrounding sea of electrons. The sea of electrons actually hold the atoms together. It makes it actually pretty strong intermolecular forces. All right, so your properties of substances, you have your metallic, ionic, and covalent. Covalent, these sharing of electrons, most of these are pretty weak intermolecular forces. That's why you have gases. That's why chlorine is a gas. Potassium chloride, this you have an ionic bonding, electron going from potassium to chlorine, creating a big lattice of an ionic compound. So very strong intermolecular forces. Metals are kind of the same way, but it's not held together by positive and negative charges. It's that negative electron moving around through all of these positive charges, holding it together. All right, your metallic properties, they are highly electrical and thermal conductivity. So they allow electricity and heat to flow through them very easily. And it does that because of the freedom of electrons to move throughout all the metal atoms. It can carry electric current with it very easily because of the movement of electrons. Luster, second one. This one's kind of interesting. It's kind of like the photoelectric effect. Metals contain many orbitals separated by extremely small differences in energy. There's not much of a difference in energy between the p orbital and the d orbital. So electrons can jump up by an energy level very easily in metals. When light hits it, it'll move up, get into the excited state, fall back to the ground state, and what you see is that luster and the light given off by the metal when it goes back to the ground state. That is why it has this luster. It's that real small difference in energy between energy levels. All right, malleability is the ability of substance to be hammered or beaten into sheets. Kind of goes along with ductility. It can be pulled in a wire. Why? Because the bonding is the same in all directions throughout the solid. You have the sea of electrons, and what it does is it allows one plane of metal atoms to actually slide past another without breaking. Much less rigid than what an ionic compound would be. All right, your metallic bond strength varies with nuclear charge, the number of electrons in the electron sea. So those are two things it depends on. What the positive charge is going to be and how many electrons are in that electron sea. So the heat of vaporization, it's the amount of heat needed to vaporize. That means go from either a solid liquid to a gas. The heat of vaporization, it's lower with a higher nuclear charge. So the higher the number of protons, the lower the heat of vaporization. It doesn't take as much heat to vaporize it. The more electrons, though, the higher the heat of vaporization.